And also I would like to thank the Institute for the support and also for the hospitality. So I'm going to speak about some results using some fully nonlinear equations. Okay, many people here spoke about fully nonlinear equations, and I will, okay, it will help me because some of them already said a lot of things I will use in my talk. So what are the motivation? The motivation are the study of the links between some algebraic or analytic properties of the curvature and the topology or the geometry of the underlying manifold. So I'm going to give some example. Maybe the most classical one is the so-called Bonnet-Myers theorem. So if you take a complete manifold, you assume that the dimension is greater than 3. And you assume that you have a positive lower bound on the Ricci curvature, then your manifold is a compact one. You also know that the fundamental group is finite, and you also have a bound on the diameter of your manifold. So another classical example is the Klingenberg, Berger, and Rauch theorem. So you take a compact manifold which is simply connected, and you assume that you know the range. So here kappa is the sectional curvature. So you know the range of the sectional curvature, and you assume that it's between 1 and 4. Then in this case, your manifold is homeomorphic to the sphere. So let me give a short remark. So recently it was proved by Simon Brendel and Rickson that if you assume only that the sectional curvature is positive and that you have a ratio between the minimum of the sectional curvature and the maximum, which is 1/4, then your manifold is diffeomorphic to a spherical space form. And also, there is in the same vein, there is also a result by Laney and John Wolfson. Okay, so maybe some more examples. So another now classical example is the very famous theorem by Hamilton on the Ricci flow, the first result historically using the Ricci flow. So you take a tree manifold which is closed, means compact without boundary, and you assume that the Ricci curvature is everywhere positive. Then you can prove that the manifold is diffeomorphic to a spherical space form. Or let's say that the universal cover of your manifold is S3. Now, if your manifold is four-dimensional, you still assume that you have a closed manifold, and you assume that the scalar curvature R here stands for the scalar curvature, and you assume that you have a pinching between the veil part of the Riemann tensor, the Ricci traceless part, and the scalar part. If you write your decomposition of the Riemann tensor, so you have the veil part, the Ricci traceless part, and the scalar part, and you assume that you have this pinching, then in this situation, what you can prove is that your manifold is diffeomorphic to either S4 or RP4. Okay, so I'm going to write this pinching condition because I will need it after. So this is by square plus 2 times. So for the traceless Ricci, I will write E strictly less than 1/6 times the square of the scalar curvature. So some years ago, Alice Chang, Matt Gursky, and Paul Young gave a conformal version of this result, of the result of Margerin. Let me just show you once again the result of Margerin. So they gave a conformal version of this theorem. I will explain what conformal version means. So you introduce, I think that Sophie Chen already defined this invariant, so the Yamabe invariant, which is related to the conformal class of the metric. So bracket G is the conformal class of the metric G. So this is the infimum of of the integral of the scalar curvature over, okay, you have to normalize, so you normalize by the volume of the manifold to some power. So this is in order to have something which is scale invariant. So of course, this is a conformal invariant. It only depends on the conformal class of G. So now you consider the Scouten tensor, which is Ricci minus 1 over 2n minus 1 times the scalar curvature times the metric. Be careful, because in Sophie's talk, the Scouten tensor was not exactly this one. She put 1 over n minus 2, so it's not relevant here. It doesn't matter, but okay, some people put a constant in front of the Scouten tensor and some others not. Okay, so you can view it, of course, as an automorphism on the tangent space of M. It's, of course, symmetric, and you denote by lambda 1, lambda n the eigenvalues, and you consider the second symmetric function of the eigenvalues of the Scouten tensor. Okay. So what is the statement of Cheng, Gursky, and Young's theorem? So you take your four manifold, which is still closed, a closed one, and you assume that the Yamabe invariant is positive. Okay, so this condition, Yamabe positive, is a conformal invariant condition. And you assume that you have a pinching between the integral of this sigma 2 function and the veil part of the decomposition of your Riemann tensor. Then you can say that your manifold is diffeomorphic to either S4 or RP4. So as I just told you, this condition here is, of course, conformally invariant. It only depends, since the Yamabe invariant only depends on the conformal class. So it's a condition only on the conformal class you are working with. So it appears that in 4D, the integral of sigma 2 is also a conformal invariant. It only depends on the conformal class. This is a result by Jeff Biaklowski. And also, the Weil square times the volume is a pointwise conformal, is pointwise conformal invariant. And it appears that if you integrate the condition in Margerin result, you obtain exactly this condition here. So this is the reason why I called it a conformal version of Margerin results. So how does the proof of this theorem runs? So you assume that your Yamabe invariant is positive, and you assume that you have this pinching here. So the way you prove this is to prove that you can find in the conformal class of G a metric for which you have the pointwise condition. So the story is to go from the integral condition to the pointwise condition. Okay? So the question is, so this was for, I insist on this fact, this is for dimension 4. So the question is, what about other dimensions? So let me quote state the first result. So this is a result by Giovanni Catino and myself. So you take a three manifold, a closed one, and you assume that the scalar curvature is positive. You also assume that the integral of sigma 2 is non-negative. So if you write sigma 2 in 3D, so sigma 2 in 3D is exactly this one, minus 1 over 2 times the square of Ricci plus 3 over 16 times the square of the scalar curvature. So if you write this, you replace by this, so you get this condition. The condition is exactly the integral of Ricci square is less than 3/8 times the integral of the square of the scalar curvature. Then what you can prove is that your manifold is diffeomorphic to a spherical space form, or if you prefer, the universal cover of your manifold is S3. So a short remark. Oh, sorry. This result was also obtained by Yuxing Ge, Shangshu Lin, and Guofang Wang under the assumption positivity of the scalar curvature and the positivity of the integral of sigma 2, which is a bit stronger than assumption than in our theorem. Okay, so perhaps yesterday Pengfei said that today was a hard day, so maybe it's better not to give proof. So I will try just to give some idea of the proof very quickly, and okay, I will not insist too much on the proof. So the story is exactly the same as in Chang, Guskey, Yang theorem. What you want to do is to prove that under these assumptions here, you can produce a nice metric. And what is a nice metric in view of Hamilton's theorem? A nice metric for us will be a metric for which the Ricci curvature is positive. If we can produce a metric for which the Ricci curvature is positive, so we can use Hamilton's theorem and say that the universal cover of the manifold is S3. So the goal here is to prove that under this assumption, we have a metric in the conformal class of G having a positive Ricci curvature. So basically, the proof of this result follows the lines of a result by Matt Gursky and Jeff Wiaklowski in 4D. So the proof is exactly the same. The only difference is on the lower bound. I will explain where. So consider this tensor AT, which is basically in 3D the Schouten tensor, and instead of putting a 1 here to have the Schouten tensor, you put a parameter T. So if you take G tilde, a conformal metric, which is written e to the minus 2u G, then look to the book of Bess, for example. So you have a formula that gives you this AT for the new metric, the metric G tilde, in terms of AG of T, right? So your manifold is a compact one, and you know that the scalar curvature is positive. So by compactness, it's very easy to see that you can find a delta, possibly negative, but it doesn't matter, such that this AG delta is positive definite. So we fix this delta in such a way, such that this AG delta is a positive definite, and we call F sigma 2 of this AG delta, which is, of course, a positive function on M. So what is the equation we study? Sigma 2 of AG UT. So what is this? What does it mean here? So we consider a family of equations. For each parameter T bigger than delta, we consider this equation. So for each T, we're looking for a solution UT. And what is GUT? GUT is this metric with UT here. Okay, this is the metric having UT as a conformal factor. Okay, so of course this is because of this formula, as explained by many speakers, this is a fully nonlinear equation. So you consider this set S, which is the set of all parameters T between delta and 2/3, such that you have a solution, a C2 alpha solution to this equation, sigma 2 equal to F e to the 2ut. But you ask for solution having positive scalar curvature. Okay, so this is our set S. So the idea is to use a continuity method. So this is the set S. Okay, so it's very easy to see that S is not empty because delta, of course, is in S, because when t is equal to delta, ut equals 0 is a solution of the equation. Okay, maybe I should go back to the equation. So if t is equal to delta, because of the definition of f, ut equals 0 is a solution. So S is not empty. So S is also an open set. Okay, you can see it by, okay, you compute the linearization of the equation, and you can show that it's invertible. Okay, so this is still the set S. So you want to actually you want to prove that that S is equal to the interval delta 2/3. So what you are going to prove is that the set S is open and closed. So for this you need some a priori estimates. So having an upper bound is easy. So it's not very difficult. So the gradient estimates, it's due to Pengfeng Guai and Guofeng Wang, and also Aobang Li and Yan Li. So the problem here is the lower bound. I will go back to this after, and this is the main difference between this situation and the work of Matt and Jeff. So once you have the upper bound, the gradient estimates on the lower bound, you can get the C2 estimates, and this is also due to Pengfeng Guan and Guofeng Wang, and also Li and Li. And then after using works by Krylov and Evans, you can go to the C2 alpha estimates. So the point here is how to get the lower bound. So the difference between this situation and the situation in the paper of Matt and Jeff is that in 4D, this quantity here is conformally invariant, as I explained before. But in 3D, it's not. So it's more, it's a little bit more complicated, so you have to compute. So you compute the integral of sigma 2 for your new metric, G tilde. So you have this bad expression. So you know that if you know that the Schouten tensor with parameter t, which it's not exactly the Schouten tensor, but let's call it Schouten tensor with parameter t. If you know that it's in gamma 2 plus, gamma 2 plus is the set for which you know that the trace sigma 1 and sigma 2 are positive. Then in this situation, so you have these two estimates here, by above and both by above, by below, sorry. And then using this and putting it into this formula here, you obtain this estimate. And then what you do, so you use this Young inequality, very simple. And what you get is that the integral of e to the 4 ut is bigger than this. So your assumption is that this guy here is non-negative. So this is our assumption. And it turns out, so P2 here is a polynomial of degree 2 in T, okay? And it turned out that when T is smaller than 2/3, everything is nice, and you can get a lower bound on ut, taking the logarithm of this quantity. And okay, the story is that if T is bigger than 2/3, this will become negative. And it's good enough to have 2/3 because, and this is the key point here. Okay, you know that if sigma 2 of A1 of some metric is positive, so you also assume that the scalar curvature is positive, then it implies, okay, this is in 3D. If you know that the scalar curvature is positive on sigma 2 of the Schouten tensor, the real Schouten tensor is positive, then actually you know that the sectional curvature is positive. So say which is positive. So with this method, we cannot reach t equal to 1, because if t is too big, this becomes negative, and then we cannot get a lower bound on ut. But if t is not bigger than 2/3, then it's okay. And actually, it appears that this is also true if you take 2/3 here. If the scalar curvature is positive and sigma 2 of Ag with parameter 2/3, you can still say that the Ricci tensor is positive. So here it's everything is okay. So we can reach here in our set S. We can reach this 2/3 here. So we have a solution of the equation. I can go back to the equation. So we have a solution for t equal to 2/3, since this function here is positive. And of course, we know that R of G U 2/3 is positive. We can use this fact and say that, okay, the metric G of U 2/3 satisfies this, and then we use the Hamilton theorem. Okay. So this is the proof of this theorem. Okay, so the result I just proved as a big default, actually. The default is that the integral of sigma 2 in 3D is not conformally invariant, right? It's true in 4D, but in 3D it's not true. So we try to get, let's say, a conformal version of this result. So let me say that it's not really conformal. This is the reason why I put this here. Okay, consider the Panitz operator in 3 dimensions, which is written in this way. So this is the Panitz operator in 3D. So Q is the Q curvature. So the expression of this Q curvature in 3D is this one. And the important fact here is that this Panitz operator is conformally invariant. It means that if you take a metric G tilde, which is conformal to the metric G, with this factor U to the -4, then you have a very nice relation between the Panitz operator for the new metric G tilde in terms of the Panitz operator for the original metric. So what is the result here? So assume that assume that the Yamabe invariant of sorry, here there is a mistake. You have to put strict here. You assume that the Yamabe invariant is positive, strictly positive. So you assume that the Yamabe invariant is positive. So this is a conformally invariant condition. And you assume that in the conformal class of G, you can find a metric for which this Q curvature here is bigger than 1/48 times the scalar curvature square of this metric. Then, in this situation, your manifold is still diffeomorphic to a spherical space form. And okay, what is the relation between this theorem and the previous one? Okay, take this condition here. So you know that the Yamabe invariant of your conformal class is positive. And you know that you can find a metric for which you have this inequality. So Q of G prime is bigger than 1 over 48 times the scalar curvature square. So you integrate this, this relation with respect to G prime, of course. So it's a very simple, oh, sorry. Oops. So it's a very, very simple computation. You use the expression of Q. And this implies that the integral of sigma 2 of G prime, A G prime, is non-negative. Okay? So in order to use the first result, now what you have to prove is that actually the scalar curvature of G prime is positive, right? So how do you do this? So consider the conformal Laplacian, which is LG is minus the Laplace Beltrami operator plus 1 over 8 times the scalar curvature. So you compute, okay, so this is for G prime, of course. So you compute LG prime of RG prime. And using this condition here, okay, you have the, oops. So you already have the Laplacian of the scalar curvature here. So if you compute this this guy here, what you can show is that this is, using this assumption here, what you can show is that this is non-positive. So using a lemma proved by Margerin, since you know that the conformal class has a positive Yamabe invariant, this implies this, together with the fact that the Yamabe invariant is positive, this implies that the scalar curvature is positive, right? So now you can use, you know that the integral of sigma 2 is non-negative, and you know that the scalar curvature is positive, so you can use the first theorem and you have the conclusion. So let me go back to this condition here. No. No, it's not. This one is a little bit stronger. But you need 1 over 48 in order to have this when you integrate. Okay, so let me go back to this condition. As I said before, because of the expression of sigma 2 in 3D, so you can write this in this way. So the question is this 3 over 8 here optimal? So for example, if you take S2 cross S1, if you take S2 cross S1, you will have that the integral of Ricci square is equal to 1 over 2 integral of R square. Okay? So in some sense, we can think that maybe the optimal constant you can put here in order to have the same result, the same rigidity result here, is 1 over 2. And actually, this is not true. The situation is more complicated. So this is what I said. So you take S2 cross S1. If you compute the integral of Ricci square, this is equal to 1 over 2 times the square of the scalar curvature. And recently, Giovanni Catino and Luca Di Cerbo, they proved using a construction we made with many Italian people in a totally different context, which is the study of the entropy functional of Perelman. So they use this construction to prove this result. So take S2 cross S1. You can always construct, and you take a epsilon, let's say small. You can always find a metric on S2 cross S1 such that the integral of Ricci for this metric G epsilon is smaller than this quantity times the integral of the square of the scalar curvature. And the scalar curvature of this metric G epsilon is also positive. And the interesting fact here is that for epsilon small, this is strictly less than 1/2. So it means that actually the best constant you can put in your pinching is not 1/2. It's smaller than 1/2. So for the moment, we don't know exactly what is this optimal value. My guess is that the optimal one is 3/8, but okay, we cannot prove it for the moment. We're still working on this. Yeah. Yes, this is for small epsilon. Yeah, yes. I said that it's for small epsilon. Yeah, you're right. Yeah. Okay. So this was for 3D. So now consider an higher dimensional manifold, dimension equal to n with n even. And okay, you consider the sigma n/2, which is exactly like sigma 2, but here you take eigenvalues going from 1 to n/2. So there is this result by Jeff saying that if you assume that your manifold is locally conformally flat, means variable equal to 0 everywhere, so you have a relation between the integral of sigma n/2 and the Euler-Poincaré characteristic of your manifold. Okay, so there is two other results, two very interesting results. Both of them are due to Matt Gursky. So the first one is, okay, take a four manifold and you assume that it is locally conformally flat with positive scalar curvature. And you assume that the Euler-Poincaré characteristic is equal to 0. Then you can prove that your manifold is conformally diffeomorphic to a quotient of S3 cross R. Okay, historically, this was the second one. The first one is the one I'm going to state now. So this theorem is older than the previous one. So take M of dimension 4 and 6. You still assume that it's locally conformally flat, and you assume that the scalar curvature is non-negative. And now you assume, in the previous one, the Euler-Poincaré characteristic was equal to 0. Here you assume that it's positive. Then your manifold is conformally diffeomorphic to Sn or Rpn. Okay, so the question is this result true in higher dimension? So in his paper, Matt made the remark that this result is not anymore true in higher dimension. So you take an hyperbolic 4 manifold and you consider the product of S4 with this hyperbolic 4 manifold, and you will get a locally conformally flat manifold with non-negative scalar curvature and positive Euler-Poincaré characteristic. And of course, it is not conformally diffeomorphic to the sphere or the projective space. So So the question is it possible to give the same kind of result in higher dimension? So the answer is yes. So you take an even dimensional manifold, still locally conformally flat, with positive scalar curvature, and you assume that the Euler-Poincare characteristic is positive. So Euler-Poincare characteristic positive in view of Jeff result means that the integral of sigma n over 2 is positive. So in this, under this assumption, you can find T naught, which is strictly less than 1. This is important. Such that, okay, maybe I should write here what is, I said it before, but I should recall it. What gamma plus n over 2 is the set of all lambda 1, lambda n, such that, so lambda 1 of lambda 1, sigma 1, sorry, lambda n is positive up to sigma n over 2 of lambda 1, etc., lambda n positive. So you assume that all the symmetric function of the eigenvalues of A, T naught, are in this set. Okay? So under this assumption, you can prove that actually your manifold is diffeomorphic either to the sphere or the projective space.
Wait, so your A, T naught, I forget now. That's you subtract. So is that, that's, you're taking the sometimes and adding a little bit, something that's saying it's impossible?
No, you assume that the eigenvalues of this guy here are in this set here.
No, I know that. Yeah, the definition of A, T naught, I forget.
Ah, yeah, it's still, okay. It's it's still the Scarton tensor with the parameter T here.
T's there, okay.
It's the Scarton tensor, and instead of putting 1 here, you put a T. So you assume that AG T naught, okay, with T naught here, is in this this set here. AG1, you mean? No, of course not. No, it's weaker. And this is actually what I wanted to say. So this does not imply that AG of 1 is in this cone. It's weaker. It does not imply, for example, that the Ricci tensor is positive for G. It's weaker. So, I'm going to finish very early. You're lucky. So let me just mention that the same kind of result in the same spirit, but not exactly the same context, was obtained by Pengfeng Guan, Shangshu Lin, and Guofang Wang, under the assumption, okay, still even dimensional manifold, locally conformally flat, positive scalar curvature, positive integral of sigma n over 2. This is this condition here. But they assume that AG1, so with the parameter 1 here, is in this cone. So they ask for the positivity of all this symmetric function up to n over 2, sorry, minus 1. And they have the same conclusion. Actually, with our method, we can also prove their result using the same method. Okay, so I stop here.
So in the three-dimensional case, do you know anything about the eigenvalues of the Hamilton data under that assumption?
No. Actually, you already asked me this question 6 months ago, but still no answer. more than 6 months ago in China. You asked me for. I thought about this, but no, I'm unable to say something about the eigenvalues. Yeah.
Going back to your first theorem, and you because you assume the integration of sigma 2 is larger than equal to 0, right?
Yeah.
And can you assume that you take supreme all those metrics with characteristic plotting and no plotting or no more like that? That's plotting. That will be conformal invariant, right?
Yes. Actually, I tried, but